All right, so now we got to talk about acid-base equilibrium and a very important concept in this chapter, which is going to be called pKa. So let's dive into exactly what this means. One of our goals is going to be to quantitatively compare acids. All right, so using the pKa is how we're going to do it, and I'll show how that's done in a second. But that's going to be how we can measure acid strength. This acid is stronger than this acid, and we can tell that quantitatively using a pKa. And then once we figure out how pKa's work, we're going to work on qualitatively assessing acid strength. So what are some features in a molecule that would lead one to be stronger, a stronger acid than another molecule? All right, so now let's derive this quantitative method for determining acid strength. Cat is climbing up the wall. First thing we got to do, so this is a generic equation for some acid mixing with water. In this case, water is playing the role of the base. That would make this species my conjugate base. And then I have my conjugate acid, the hydronium ion, right? So this is just a generic equation for what happens when you are generic reaction, balanced chemical equation for when you're mixing water with an acid, okay? So all reactions, remember back to general chemistry, have an equilibrium constant associated with them. So KEQ, what I want you to remember is products over reactants. So if we fill that in for our particular equation here, the products would be the conjugate base. Oh, I got a kitty walking across the computer. Say hi. Hopefully we're still recording. I think so. Okay, and then times the other product here, that hydronium ion. And my reactants in this case are the acid, and again, this is just this generic form, HA, and water. Okay, so this is the equilibrium constant, the equation for the equilibrium constant for this reaction. Notice that if KEQ is less than 1, that's a reaction that favors the reactants, this side of the chemical equation, right? Because this number here is then going to be less than 1. So that means that my denominator is going to be bigger than my numerator. Likewise, if the opposite is true, and KEQ is greater than 1, that's going to be a reaction that favors the products, because the numerator in this equation is going to have to be bigger than the denominator, right? So that's how the value of the equilibrium constants. And if it's way bigger than 1, then that's a reaction that super duper favors the products. Okay, so this is sort of part of the idea that we're going to be pulling on today. Now, one thing I want to point out, get rid of these markings here, is that in this term here, the concentrate in our equilibrium constant equation, we have this concentration of water term. In most solutions that you prepare, the concentration of water is going to be way, way bigger than the concentration of everything else. So much so that it basically remains constant throughout the experiment. It's always about 55 molar. Whereas your concentration of acid is going to be like on the order of like 1 molar, maybe 10 molar if it's crazy, crazy concentrated, but way, way less than 55. Okay, so instead of using the equilibrium constant to talk about a reaction, we actually use something called the Ka. So let's take a look at that real quick. So let me get rid of this here. So here is the Ka for this reaction. Notice it's the exact same thing as the KEQ, except that water term has been removed. So we can say that the Ka equals the KEQ times the concentration of the H2O. And again, since that concentration of H2O is, we think about it as being constant, we like to just refer to things as the Ka, okay? So this is the formula that we're going to use to talk about our chemical equations. And again, notice that if I have a Ka that's way bigger than 1, that's a reaction that very much so favors the products. Ka less than 1 will favor the reactants. And then to make things even more convenient, we actually use what's called a pKa, which is when we take the Ka and we take the negative log of the Ka, that equals the pKa. So it's just putting the Ka on a logarithmic scale. Kas can be anywhere from really small numbers like 10 to the negative 30 to really large numbers like 10 to the positive 30. So it's easier to talk about these things on a log scale. I think log scales are something that I don't know that I was really all that great with when I was a sophomore in college or in y'all's position. Now they're great, but you know, it's one of those things that you might want to review what exactly a logarithm is. I put a link to the Wikipedia page that talks about logarithmic identities, so you guys can get some refresh your memory on what exactly those are. Okay, but this is how we're going to be assessing acid strength, is by looking at these pKa's. These pKa's for every acid are going to be tabulated in an appendices. There's one in your book. I've actually put one that I like even more to be able to be downloaded off of Canvas that's much more complete than the one in the book. And if you run through, what you'll see is a list of all these different acids and their associated pKa's. Okay, so this is the definition of a pKa right here. It's the negative log of a Ka, and of course a Ka relates to the chemical equation of what happens when you take your acid and you mix it with water. Okay, so this is an example of one of those pKa tables. So how could I use a pKa table to assess acid strength? So one of the things that I just want to point out real quick is how logarithmic scales work. For every unit that you jump on the pKa scale, so +1 on the pKa scale, that corresponds to a magnitude of ×10 of your Ka, right? So if I increase my pKa by +1, that's the same thing as if I took my pKa and multiplied it by 10. Okay, so that's just something to keep in mind. All right, so let's look at this here. We have all these different acids. You got the actual molecular structure for them, and then the pKa's that correspond to those acids. So we can use pKa's to determine the relative strength of an acid, okay? So for example, we know that hydrochloric acid is a strong acid compared to something like ethanol, which is not necessarily thought of as an acid. Well, that information is encoded in these pKa's. Specifically, the lower the pKa, the stronger the acid, okay? So hydrochloric acid, again, that classic strong acid, has an incredibly low pKa of -7 compared with ethanol, which has a pKa of 16. So if I wanted to identify which acid was stronger, I would look at my list of pKa's and figure out which one has the lower pKa. Lower pKa means stronger acid. And real quick, what does it mean to be a stronger acid? What does an acid do? An acid donates a proton. So the stronger the acid, the more likely it is to get rid of that proton to whoever it can, right? Strong acids like to get rid of protons. Okay, so then let's just do this simple example here. See if you can't tell me which one's going to be the stronger acid, ethanol or what's called tert-butanol. So the first thing we're going to do is look on our table of pKa's. We're going to find ethanol, and we're going to find tert-butanol, and we're going to ask ourselves which one has the lower pKa. So in this case, ethanol is the stronger acid. And notice that both of these are alcohols. We wouldn't necessarily think of them as acids, but again, we're talking about who's going to play the role in a chemical reaction here. And so indeed, we can use these pKa's to compare the acidity of different molecules, right? Which their tendency to get rid of that proton or donate that proton. but we can actually use it to tell relative basicity as well. One of the things you're going to hear me say over and over again is if you're a really good acid, then your conjugate base is a really crappy base. Okay, these two go hand in hand with one another. The strongest acids have the weakest conjugate bases. And likewise, the weakest acids have the strongest conjugate bases. So if we want to tell how strong of a base a compound is, we're going to look at the pKa of its conjugate acid, right? So if I'm going from acid, then that would be my conjugate base, but I can also go the other way and say, these are my bases, and then this column over here are the conjugate acids. All right, so this is also how you can tell basicity. This is why this one skill from the previous lecture is really important. Given a base, can you figure out what its conjugate acid is? That's going to be really important because you're going to need that skill in order to be able to compare basicities by looking up these molecules on this pKa table. So let's look here. I have two different molecules here, and I want to know which one is the stronger base. This guy is what's called an ethoxide ion. It's ethanol, but it's been deprotonated. This is what's called a phenolate ion. Phenol is this alcohol here after it's lost a proton. Okay, so if I want to compare the basicity of these things, the first thing I got to do is figure out what the conjugate acid of each of these molecules are. Remember, the conjugate acid is my base after it's accepted a proton. So in this case, my conjugate acid is going to be ethanol. And down here, my conjugate acid is what's called phenol. So then I can go to my pKa table here and I can look up ethanol and I can look up phenol. So first of all, which one's the stronger acid? That would be phenol. But remember, these things are going to be inversely proportional in terms of stronger acid means a weaker conjugate base. So if I want to know which one's the stronger base, I'm actually looking for the weaker conjugate acid. So in this case, my stronger base will be the ethoxide ion because its conjugate acid has the higher pKa. Okay, so pKa's can not only be used to tell the relative acidity of molecules, but also can be used to tell the relative basicity of molecules by comparing their conjugate by comparing pKa's of the conjugate acids of those bases. And again, just what does it mean to be a strong base, right? What does it mean to be a base that accepts a proton? So a really strong base is going to go in there and grab a proton off of anything, whereas a weaker base is going to be a little bit more reluctant to do so. All right, so then we'll talk, practice these skills of being able to determine relative strength and acidity and basicity, and then we can go on to the next thing that we can do with pKa's.